drawn by Jess. So I will, let's say, go to the formulation, to the numerical formulation, and I will present a method that we call the linked Lagrange multiplier technique to prescribe essential boundary conditions, in that case only for elliptic problems on embedded meshes. So that's the outline of the talk, and going to the introduction, the setting of the problem is I mean, I don't have to explain anything. Just for notation, we have a fixed mesh, a fixed background mesh, and we have a boundary gamma where we want to impose a certain boundary condition u equal to something on that embedded surface. So, obviously a possible strategy would be local remeshing. I wanted to keep this slide because this is something that is very often, let's say, forgotten, but local remeshing is perfectly possible. And in fact, the main drawback of local remeshing is that you have a variable number of degrees of freedom, and that's what you want to avoid. And that's particularly important in the case of moving domains, but that's always a possibility that we have there. Okay, so the two main possibilities that we have is the use of Lagrange multipliers, which is the basis of the fictitious domain method, for example, or Nietzsche's method. So those are the two most classical methods to prescribe essential boundary conditions in embedded meshes, in surfaces that are embedded in a certain background mesh. There are other methods, but I think those two are the most relevant. So what I will present now is somehow something that has the properties of Nietzsche's method, but starts from the concept of Lagrange multipliers, as we will see. So, which is the, let's say, problem of Nietzsche's method? The problem is that you have to define, let's say, a term that scales as a diffusion in general, and a length scale, an h, an element size, and maybe that's not that clear in all cases. So, in the method that I will present, we don't have to choose any length size, any element size, and we don't have to choose any diffusion coefficient, so to speak. So, the objective is to prescribe the boundary condition u equal u bar on gamma, or in general in an abstract problem, d of u equal d u bar, as we will see. And we don't want to add new degrees of freedom to impose that. So, I mean, in principle, Lagrange multipliers have the disadvantage of requiring more degrees of freedom, so we don't want to do that. And the idea of our method is that, in fact, we will introduce a Lagrange multiplier, but we will relate it to the main variable, to the primal variable, if you wish. And we will condense that Lagrange multiplier in terms of the primal variable. So, that means that at the end of the day we will have a problem that has the same degrees of freedom as for Nietzsche's method. I mean, no more. Okay, so let's explain. I will explain the idea of that, or the organization of the talk is that I will explain the method for an abstract problem. That I will, let's say, try to explain that in some detail. It's easy, as we will see, and then I will very briefly explain how to apply it to four more problems. So Poisson, Darcy in primal form, and Darcy in dual form, and Maxwell. We have also applied that to Stokes and Navier-Stokes, of course, but I will not explain that. So let's explain the method. So I will try to explain a new method, or a method that we have been developing in the last, let's say, 5-6 years. So suppose that we have an elliptic problem of the form L u equals f. You can have different components, of course. So, for example, in the case of Darcy, U has the velocity and the pressure components. In the case of Maxwell, it has the magnetic field and the pseudo pressure. So U is the unknown, we want to solve that problem, and the boundary conditions, the essential boundary conditions have to be written in this form because maybe not all the components of U need to be prescribed. So d of U equals du bar. Okay, so suppose that the problem is elliptic, the L is symmetric and positive definite to make things simpler, and the solution of that problem is the minimization of a certain functional f. If we take the first variation of that functional, what we have to solve is this variational problem, b of u delta u. Here I use the symbol delta u for the test function, or the virtual u if you wish, equals to the right hand side. And the bilinear form u consists of a certain duality between L of u and the test function. Okay, so that's the abstract problem that we want to solve. One possibility to impose the boundary conditions that here are imposed in a strong way, let's say. So we have to minimize that functional on the set of functions that satisfy the boundary condition u equal u bar. So that's what that x u bar means. Yes, that's introduced here. An alternative is the use of Lagrange multipliers to prescribe the boundary conditions, and that consists of optimizing this functional, the functional that is f of u, the functional that we had before, minus the a certain multiplier multiplying the difference between d of any function v minus d of the prescribed condition u bar. So the optimization of this functional has two unknowns, the primal variable, the original unknown u, as well as the Lagrange multiplier lambda. And if we want to optimize this functional in brackets, we are led to these two problems. So this is a classical saddle point problem where we have to solve for u and lambda. That's standard, well known. And now when we go to the discrete problem, in principle everything is simple. We construct finite element spaces for u, which are represented by this x bar, and for the space of Lagrange multipliers, which is the dual of a certain space of trace functions on the boundary. So that's the space where the problem is posed. Okay, in principle this is very easy, so just have to construct those spaces, but as we know, the problem is that those two spaces have to satisfy a certain implicit condition that is not trivial to satisfy, first, and second, that we have more degrees of freedom than those that we had at the beginning. At the beginning we only had those degrees of freedom of x, and now we have the degrees of freedom of x and the dual of gamma h. So what is the idea the essential idea of what we propose? The idea of what we propose is, okay, we will use a Lagrange multiplier method, but we will link that Lagrange multiplier to the primal variable. Because we know that multiplier has to be the trace of the flux of the primal variable. So what we do is, since we know that would be, let's say, an a posteriori result, we put it in the beginning in the functional that we are going to optimize. So what we do is we enlarge the original functional that we want to optimize by this term. So here tau n would be the Lagrange multiplier, and we say that that is going to be the trace on the boundary gamma of a certain function that is, in a least square sense, the flux of the primal variable. Okay? So this is just imposing that tau is equal to the flux of the primal variable. The flux, of course, depends on the problem, and the let's say Lagrange multiplier that appears is nothing but the trace, the normal trace of that function tau. Okay, and in principle, n is sufficiently large, but greater than 1 suffices in most of the cases. So we don't have to choose n. 1/2 is usually enough. Okay, and now the problem that we propose is to optimize this functional, where sigma, take into account that sigma now is, let's say, a volume variable. It's not defined on the boundary gamma, but on the whole domain omega. Okay, so if you obtain the two Euler-Lagrange equations of the previous functional, you end up with this expression. That's easy. And the point now is, of course, in this case, we have more degrees of freedom than we had in the original problem. But the idea is that if you choose the space sigma for this new variable, the linked Lagrange multiplier that we call, adequately, and adequately means that you can take, for example, that piecewise constant, you can condense sigma in terms of u and end up with the problem posed in terms of the primal variable alone. That's the idea, okay? So you don't have, it's a linear problem, you don't have to iterate, and you have a problem with the same number of unknowns as the original one. So what is the difference with Nietzsche's method? The difference is that there is a length scale, let's say, inherent to the method. I mean, the problem scales, when you make that condensation, the term that appears that imposes the boundary conditions scale is 1/h, of course, like from Nietzsche's method, but you don't have to choose it. And that's important, for example, if you have very anisotropic meshes. That's what we wish to do for flow problems, because we want to deal with boundary layers, which is a hot topic in the case of immersed boundary methods. Okay, that's it. That's the method, essentially. Nothing else. Okay, so I will go very fast to the three examples without paying much attention, and just showing how the method is applied to these four problems. Poisson, that's the problem, that's the functional, so standard. That's what we do. The flux is nothing but k, the diffusion gradient of the unknown. Okay, so that's the flux. And here we have the normal trace of that flux. That's it. That's how to apply that for Poisson. And as explained here, we can condense one variable. We have stability in that norm. By the way, we have made the analysis of all the problems that we have. We have not only stability, but also convergence, and it's optimal. And you see that, in fact, we have a stability and convergence in the same norm as Nietzsche's method. That would be the norm in which you would prove convergence for Nietzsche's method, plus some volumetric control on that variable that we have introduced. That is a sort of volumetric Lagrange multiplier. Darcy problem in primal form. In primal form, that's nothing but that Poisson's problem. So we look for the primal variable in H1 and the dual variable in L2. So that's if you eliminate a Q from that equation, you end up exactly with the same problem as before. And the only point is that in that case we need a certain compatibility condition. We need two things, sorry, we need two things. I don't want to explain much about that, but in fact we need two things. We need, first, a compatibility condition, an if-sub condition for the space, for the approximating space for Q and the approximating space for U, as well as a new condition, that's the if-sub condition, sorry, as a new condition for that variable sigma h that we have introduced, the linked Lagrange multiplier. But this is very easy to satisfy, for example, taking piecewise constants, as I said before. So that holds for piecewise constants. And again, we have stability and convergence in the norm that has everything, has what we would have for Nietzsche's method plus this control. What about the dual form of Darcy's problem? So the equations are exactly the same, but now the primal variable is in L2 only. Of course, you have to integrate that term by part to give sense to this term. And the flux is in H dip. So that's the really interesting form of Darcy's problem. In that case, the Dirichlet condition is this one, so the normal component of the flux, and that's what we want to impose. So we do the same. We do exactly the same. We prescribe. That would be the classic Lagrange multiplier technique. But now we impose that Lagrange multiplier is equal to the primal variable. Why to the primal variable? Because that is the dual variable of the Dirichlet condition. Okay, in essence, that you would do the same as for the classical Lagrange multiplier technique. Okay, so that's the Dirichlet condition, and the dual variable now happens to be the primal variable. Okay, so that's what we do. And again, we have optimal stability and convergence. Let me go to the last example. As I said, we have the analysis of all these methods. The last example that is interesting because, in fact, we have two essential boundary conditions. This is Maxwell's problem. So, in Maxwell's problem, we want to look for a magnetic induction field U that satisfies these equations. And we have this solenoidal condition that can be, in principle, at the continuous level, it holds exactly, but at the discrete level, it is convenient to enforce it explicitly. Because if you don't enforce it, you may end up with an induction field that is not solenoidal. So, and the way to enforce it is through a sort of pseudo pressure. It's not the magnetic pressure, but a certain pseudo pressure that we have called here P, to use the same notation as for Darcy's problem and also as for the Stokes problem. So in this case we have two boundary conditions. The space where the problem is posed is H curl for U, that's standard, but that new variable P happens to belong to H1. And we have to impose as boundary condition that P is equal to 0. And of course we have the classical boundary condition for Maxwell problem, which is that the tangent component of the magnetic induction must be equal to something given. Okay? The exact solution to this problem is that P is equal to 0. That's the exact solution to this problem, which is if F is divergence free, it's easy to see that the solution is P equal to 0, because if you take the divergence of this equation, you have that the Laplacian of P is equal to 0 for divergence free F, and if the boundary condition is P equal to 0, so the solution is 0. But at the numerical level, it's important to introduce this P. Okay, so now we have two boundary conditions, and of course we will have to introduce two Lagrange multipliers, and in our case, two linked Lagrange multipliers. So what is the functional that we have to optimize? So the classical function of the Maxwell problem plus the, let's say, Lagrange multipliers applied to the Dirichlet conditions, the tangent component of the magnetic field, magnetic induction, and Q, this Dirichlet condition for this pseudo pressure. Okay, and we have two Lagrange multipliers, and we link those two Lagrange multipliers to the flux of the primal unknowns, which in this case are the primal unknown itself, U, and this curl of U. Okay, that's what you get when you integrate the parts. Okay, that's it. That's the idea. Again, you can condense, when you write down the discrete equations, you can condense the two linked Lagrange multipliers and end up with a problem posed in terms of the magnetic induction and the pseudo pressure only. In this case, well, the analysis in this case is a little bit more elaborated. Of course, you need to meet the conditions that are required in the case of classical approximation to Maxwell's problem, plus some additional conditions for these two linked Lagrange multipliers that can be satisfied. For example, here I have just written the simplest case in which those two conditions holds. First, you have to choose the first Lagrange multiplier so that the order, the polynomial order of the elements in the space of the first Lagrange multiplier is at least that of the elements in the unknown U, and the order of the elements in the second Lagrange multipliers is at least of the order of the elements in the, let's say, in the pseudo pressure. And both need to be made of discontinuous functions. So in that case, there is a condition, a compatibility condition that allows you to prove stability and convergence and all what you need to prove. Okay, and that's what I have said here. But again, what is relevant is the concept. Okay, summary and conclusions. So the main idea of the method is described here. So we consider the functional to optimize of the classical Lagrange multiplier method. That's it. But then, the important thing is that we suppose that the Lagrange multiplier is the trace on the boundary of a flux, if the unknown is a primal variable, or a primal variable if the unknown is a flux. That's obvious, because we have, I mean, always the Lagrange multiplier is the dual of the original unknown. Okay, we suppose that. And then we prescribe this condition in a least square sense. And then we link the bulk field, the main field, whose trace is the Lagrange multiplier, to the unknown. How? By adding a least squares term to that functional. The only, let's say, parameter that needs to be determined, that needs to be fixed, is the coefficient that multiplies this term, but 1/2 works in all the cases that I have shown. And after choosing the linked Lagrange multiplier as discontinuous, you can condense that new and in principle new unknown in terms of the original one, and end up with a problem posed in terms of the original one. So which are the main properties of this method? Well, compared to the Lagrange multiplier technique, the compatibility conditions are much easier to satisfy, much easier. So remember that this field is defined in the volume, not on the surface. That's important. The linked Lagrange multiplier can be condensed in many cases. In particular, you will use a linked Lagrange multiplier that is possible to condense, of course. I mean, you can use other options, but they wouldn't have interest. Compared to Nietzsche's method, the matrix that comes from the boundary terms has a wider stencil. That's something that has to be taken into account. So it involves more points. But there are no penalty parameters large penalty parameters to be chosen. and there is no length scale to be chosen, and it has an excellent numerical behavior. We have stability and convergence for Poisson. That's in primal form, that's in dual form, Maxwell, Stokes, and all the problems that I have not shown here. Okay, thank you for your attention.